5, 4, 3, 2, 1. Hey, David. How you
Hi,
doing?
Charles.
So we're here again.
Yeah, well, last time you were here, you talked about singularity. Now I'm going to talk about something completely different. So, totally different than singularity. This
cool.
Is,
so who's
Sidd
here?
Puri with me.
Sidd.
How you doing?
Hey.
All right.
So I'm a principal researcher at Microsoft Research, lead the Advanced Compiler Technology Group. Sidd works with me on this project called Accelerator.
Okay. And what's that?
So, so you probably, I don't know if you've done any Channel 9 stuff on multi-core and what's coming with parallelism. Have you?
Yes, we have.
Okay. So, so as you guys know, parallelism is sort of the wave of the future. It's the big thing that's coming up for developers. And so what Accelerator is it's an approach on dealing with parallelism. So it's a project basically dedicated to bringing data parallelism to a wide number of programmers. So data parallelism is a particular way of programming parallel machines that we think would be really useful for a lot of people.
Okay.
So Accelerator is this MSR project. We've been working on this for a couple of years, actually.
Mm-hmm.
And so you're probably wondering, what the heck is data parallelism?
Yeah, so let's dig into the problem space.
So, Sidd, do you want to talk a bit about data parallelism?
Sure, yeah.
Yeah, okay.
So people are talking about all kinds of parallelism, and it seems like most people are focusing on what's called either thread-level parallelism or instruction-level parallelism.
Okay.
So in thread parallelism, you have a whole bunch of different tasks that need to be done. Think of a server that spawns a different thread for every request that comes in.
Uh-huh.
And you can easily run a different thread on every processor or on every core. And this is great for servers, and it's great if you have a couple threads running on your client desktop. But if you have 100 cores, which they're talking about having sometime in the next few years, there's no way that you're going to have 100 different threads doing useful things all at the same time.
Huh.
So this kind of the thread-level parallelism doesn't really scale very well. The other thing people try to do is instruction-level parallelism, where on a very fine grain you find instructions that can be run in parallel. And people do this in processors. That's one of the ways that processors have been getting faster. Mm-hmm. But they've pretty much reached the limit on that as well. There's not too much evidence that that's going to get too much better.
Okay. Interesting.
So what's data parallelism?
So data parallelism.
Yeah.
So the other big form of data parallelism is data parallelism. So there the idea is that you have a whole bunch of data, and you're doing basically the same thing to every piece of data. So in the old days, they used to call this SIMD parallelism. They had special SIMD computers. So SIMD stands for Single Instruction Multiple Data. And the idea there was that you have one instruction decode unit, and that decode unit talks to all of the different data units, all the different ALUs, and they all work in lockstep, and they do exactly the same thing on all these different pieces of data. So these days we don't have SIMD chips per se anymore like they used to back then, but you can have a similar paradigm, which is SPMD, Single Program Multiple Data. So now you have all these different pieces of data, and the same program is running for each one. So for example, let's say you have you're running Photoshop, and for every pixel you want to do basically the same thing. You want to sharpen the image or blur the image, and so for every piece of data, you're gonna look at the surrounding pixels, and you're gonna take the average and something like that. And if you have the same program running on a whole bunch of different threads, then each one can be fetching different data from memory. And with a single program, you don't have to explicitly write the different thread for each processing unit. Mm-hmm. With a single program, you can harvest arbitrary amounts of data parallelism.
So another way of talking about data parallelism is when you write a C program nowadays, you write this for loop, and you tell people what you're going to do for every single instruction. You tell the people what are you going to do. So you want to add two arrays together. You write some for loop, you iterate over all the elements of the arrays, and you add them together. Well, data parallelism says, well, that's too low level, guys. We can't do that. What we're going to say is, we're going to give you aggregate operations over sets of data. That's what data parallelism is about. So we give you these operations that operate over an entire set of data. So in C, you might write this for loop, and it's really low level, and it really constrains how you can execute the code in parallel. In Accelerator, you simply add two arrays together. It's kind of like these old technologies like APL, things like that. You just say, I'm going to add two arrays together. And then it's up to us, and it's up to our system, our compiler, the Accelerator system, mm-hmm. to actually figure out how to make this stuff run in parallel. So you have to do it, and we'll have some code examples later on.
Good.
To make this really concrete. So, because we know that this sounds really vague. But, so what you're doing, though, is you're doing aggregate operations over aggregate or large sets of data.
Mm-hmm.
Okay, and this is something that we certainly, it's been around for a long time, and there's been a lot of work in the computer science community on it, but it's not sort of widespread and widely known. But if you actually take a step back, it turns out that this approach is actually used a lot in practice. So one place where it's used is databases, but the part that we think is really going to be kind of fun is if you actually look at your graphics processing unit on your PC, you have a high-end graphics card, or if you have a high-end, you have an Xbox or an Xbox 2, well, those things use GPUs. And it turns out that the GPU is a mass-market data parallel processor. That's why graphics processing units are so fast, and that's why you get such, blindingly good graphics out of these things, is that these are highly parallel computers. So what we've done in Accelerator is build a way so that, like I said, the high-level goal is data parallelism, but so what are people going to actually use in practice? And what we've actually spent the past couple of years doing is building a way to program your GPU to do data parallel programming. And so you can use your GPU to solve problems that you would never think you could solve, or that you would be quite difficult to do. And we've wrapped it all in this high-level language. So it's just a library that you download. You can use it from any managed code program. It's a .NET library you download, and you do a bunch of operations, and these are all these high-level aggregate operations. And we actually will make this stuff run on your GPU and do all the arithmetic and computation on the GPU. And the cool thing about this is that you can get big speedups from this stuff now. So if you're doing like image processing, Sid mentioned if you're doing, for example, processing a photo, you can use our system to write your algorithms for manipulating the photo, and you can get like a factor of 10 speed up here.
Nice.
So this is really cool, and you're using your graphics processing unit to do things it really wasn't designed to do, but it does them really well. And you don't have to know any of the details. There's this whole community of people out there called General Purpose Programming on Graphics Processing Units, GPGPU. There's a website, www.gpgpu.org, full of this stuff. But you have to be an expert in using the graphics processing unit. You have to learn all this stuff about DirectX, and you have to figure out how to map your algorithm into DirectX terms, and then you have to figure out how to use pixel shaders and all this other stuff. Well, we, in our project, we looked at this and said, wow, this thing's a data parallel computer. And we looked at this and said, and we know people have been looking at how to do this stuff for a long time. So we think we can wrap this stuff in a nice layer, abstract away all those details, and give people a nice layer and still get the performance that they're looking for.
Interesting. Now, let me ask though. So you're really saying you're taking advantage of the power of the GPU.
Yes.
That sort of isn't being fully utilized by the system. For example, in the UI of the desktop and whatever application you happen to run. Of course, it's going to be used a lot when you're playing games or whatever.
Yeah.
So for the general situation, there's plenty of room for this to happen.
Yes.
How is this different from what they're doing in, say, WinFX and providing a layer for people to write 3D model, really, take advantage of the same processing power in a very simple way? So is it similar? Is it different? Is there?
I don't know a lot about WinFX and what they're doing there.
Okay. That's fine. This is just a random question.
So one difference would be that in WinFX, you are using the graphics card to do graphics, which is a great use for a graphics card. There's no question about it.
Sure.
But the Accelerator project is actually much more ambitious than that. We're actually using the graphics card to do computation fluid dynamics or implementing neural networks or you name it. So we can do matrix multiplication faster than we can on the CPU, and I'm sure there are all kinds of scientific applications or
certainly
compression, video compression, sound manipulation, all kinds of things that people want to do that you wouldn't be able to do with WinFX.
Fair enough. So, and the other thing is, if we're targeted, so in the age of multi-core and the whole concurrency issue, blah, 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 you're actually moving away from the multi-core, worrying about that and just hitting the GPU anyway. So in other words, the problem with the multi-core situation, you're not taking advantage of the power of the multi-core because you're not concerned about that chip, right?
Actually,
yes and no.
Yes and no. So we actually spent a lot of time focused on the GPU, but it turns out what we're really doing is giving people a higher level programming model for writing their parallel programs. That's what we're really doing.
Cool.
So it turns out we're actually working on targeting the multi-cores now. Because what happens is you write your program at a high level, and then it's our problem to translate it down to the multi-core chips. And that's actually what Sidd has spent a fair amount of his time working on recently. And so the real answer is we're trying to give people a higher level programming model. Just like, when you start programming with Windows, people don't write all these Windows calls. They actually, use VB and they hook things up and they use widgets and all this other stuff. Well, that's what we want people to do for parallel programming. We don't want people down there in the guts trying to worry about, did I load balance this computation properly and I've got 8 processors and now I've moved to 16, how the heck do I take care of this? Like, no, you just write your code in a high level fashion using something like Accelerator. And we won't claim that Accelerator is the be all and end all. We're a research project. There's a lot more you can do with data parallelism than we've done. But it's a good start.
Excellent. Very cool.
Just to emphasize the big picture again, so the idea is that we provide a model for writing data parallel programs. And the idea is that the model is abstract enough that you can write your programs to this model, just like you write in C# and you don't care what hardware you're running on. And then when the program actually runs, it can look and see, do I have a multi-core? Do I have several chips? Do I have a really high-end GPU? And at runtime, the program can actually decide now what is the best platform for me to run this on. You don't have to know that when you write the program.
Fantastic.
This is, I'll add the words of wisdom here. This is a research project, so this is not fully baked.
Sure.
So, so we're still working on this stuff. But that's our vision. That's where we're going.
But I mean, it's clearly the wave of the future. I mean, developers really shouldn't have to worry about, concurrency. You shouldn't have to worry about it. You should be able to write your algorithms, write your code, which is a whole .NET thing, right? Concentrate on the algorithm, forget about memory. Well, concentrate on the algorithm, forget about concurrency. Forget about all the guts that happens underneath. Blah, blah, blah. That's great stuff. That's the future. So this is beautiful. So, what else is going on here? So how did you guys implement this? What is it? Do we want to talk about that? I mean, is that...
Sure. Where do we start?
I think I'd rather do a demo first, actually.
Okay, sure.
We'll do a demo and go over some code first, since I use this term aggregate operations, and that's sort of inspecific. We want to be really specific about what you do here. So why don't we do the demo first, and then we'll go over how we built it.
All right, so I'm going to pause this as we walk over. All right, so we're in demo world now. So what are we looking at?
So I mentioned earlier that one of the things that we can do is picture image manipulation, basically. So we have a demo that shows kind of the most basic kind of image manipulation. We just take an image and blur it. So it's a Gaussian convolution. Nothing really special about it. So
sure.
I've got
those are pretty vanilla.
So I've got a picture here, reasonably high resolution. And the idea is that I just want to blur it with a 5x5 pixel filter. Okay. So if I run this thing, let's see. Here it is. So can I start that over again?
Sure. Well, just keep on going. I mean, it's... Demos are meant to not work first time.
Yep.
Okay.
And this is happening because I'm using the wrong file name for the picture.
Aha.
So here we go. So this is the same image after the convolution. So this is my wife in Thailand. This is my wife in Thailand after I've had a couple beers. Looks a little hazier. So. So the interesting thing, of course, is not that it can be done. The interesting part is how long does it take to do it. So,
True, that was incredibly fast.
Right. So it's a fairly small image. I'm going to cheat a little and I'm just going to run it several times, which gives us the same effect as running it on a larger image.
Okay.
So let's say you have a really good camera and you're going to run this thing.
So which one are you running here? Is this the CPU version?
This is this. Oh, I'm sorry. Yeah. Let me run the GPU version first. Actually, that'll work better. So this is the GPU version. We run this on this picture, and it takes something like 10 seconds or so to run, if I remember correctly. So there we go. So total 10 seconds to run on this large image, but the timing that it's measuring per small image is about 6 milliseconds per image. So that's kind of our baseline. Now, if we run the same thing on the CPU, so unfortunately, this is actually going to take so long that we may not actually want to wait for it. It's going to take about 2 minutes to run,
Wow.
And overall, the difference is about a 15x difference on this particular.
Now, can we touch briefly for people who might not have a lot of understanding of computer hardware? I mean, why the GPUs these days, especially, are incredibly fast.
Mm-hmm.
I mean, how can a GPU be more powerful than a CPU?
Yeah.
Is it just because you have more power available? And what's going on here? Can you just one more time? Can you explain why this is happening?
Yeah, there's a couple of things going on. One thing is that the GPU actually has a whole bunch of arithmetic units on it. So it's not just a few like the CPU has. It's got like a dozen different full pipelines where each pipeline is basically like a small CPU. So it's basically kind of like having a 12-core CPU, give or take. But that's only one part of the puzzle. The other part of the puzzle is that a lot of the time actually goes into memory traffic. And GPUs are set up to have an incredibly large amount of bandwidth between the dedicated GPU memory and the GPU processing units. So it has a very, very thick pipe between these two pieces, and it also sets up the computation to access the memory in just the right order. So it tickles the DRAM chips just the way they like to be, and they can just stream out data very quickly that way. This is actually one of the things that we make use of in data parallelism, regardless of the underlying hardware. One of the benefits of data parallelism is that we can analyze what the memory access patterns are, and we can do exactly the same trick that the GPU does natively, namely, we can figure out how to stream the data in and out so that you're not wasting time by going out of cache.
So to give you an example of, okay, you're going to have to peer up. To give you an example, I think the number that I quote is, your typical CPU, the maximum main memory bandwidth that you're going to get is about, I think it's rated at 6.4 gigabytes per second. And if you went out and bought like the absolute latest stuff that's coming out, I think it'd be like 8.5 gigabytes per second or so. Whereas with a high-end GPU, and which card did we have in there? It was
This is the ATI X1800.
ATI X1800, which is one of the high-end GPUs out there now, one of the best ones made by, you're looking at more than 50 gigabytes per second of main memory bandwidth versus 8 gigabytes. So that's 6 times more main memory bandwidth. And so when you're processing large amounts of data that don't fit in the cache, the GPUs have a distinct advantage here. Now, and the other thing that Sid said is they have a lot more computing power in them. So they have many what they call pixel shader units. So these are pixel shader processing elements. And I think isn't it more than 12? Isn't it more like...
It depends on the card.
Depends on the card,
12,
but...
16, I've heard it.
Yeah, well, I thought the latest ones were up to 48.
Okay,
so they have a lot of arithmetic units on this. So for certain kinds of applications, they're going to do really well at this point. Now the downside, before you think GPUs are the holy grail and that's what you're going to program to, the GPUs have only 32-bit floating point arithmetic. So if you're doing certain kinds of problems that require 64-bit floating point arithmetic, or you're doing integers right now, it's a little hard to use them to do that stuff. Your integers had better fit in the floating point numbers that they have. But what we see coming down the road is we see more generality there. So we see more generality in the operations the GPU can do. Now that isn't to say that you couldn't take the same stuff and transplant it into a CPU. That might be something that happens down the road.
Totally. Now when systems do come out that have, 64 cores in a processor, I mean that's an incredible amount of computing power, much more than any GPU. Are you guys going to take advantage of that?
Absolutely.
Of course.
Yeah.
So you figure out what's the smartest way to go, and I don't have to worry about it.
Yep.
That's our hope.
But now let me ask you this, though. Isn't it more complex for you to write against a multi-core system, given the tools that you have,
yes, it
versus
is.
hitting the GPU? So you're going to have to do more work on your end.
There are different kinds of complications, I guess. On the GPU, there are complications just because the programming model is not really designed for general purpose programming, and we have to jump through all kinds of nasty hoops, deal with system crashes and whatnot, because we're just doing stuff that wasn't really intended. On the CPU, the challenges are more technical, which is why, as David keeps reminding us, where this is still the CPU side is still very, very much active research. We don't have all the answers yet of exactly how to manage cache, basically. That's basically what it's all about on the CPU. But we're certainly working on it.
Interesting. Have you talked to the CCR people?
Who are the
The
CCR?
coordination currency runtime. They're in robotics.
No,
They've
we
done
haven't.
some
No, we
really,
haven't.
really. I highly recommend it. They've done some really interesting work with helping developers write multi-threaded code without actually spawning threads explicitly. And they do a lot of that magic for you underneath, and you're basically dealing with. Anyway, contact those guys. Giorgio, he's over there, robotics team.
Okay, cool.
Anyway,
Cool, thanks.
So I see we finished running the CPU.
Oh,
so
excellent.
it finally finished, huh?
Yes, and here you can see, if you look at these numbers, we've got 6.5 milliseconds versus about, 100 milliseconds. So you can do the math, it's about 15 times.
Wow. I wanted to show some code because I like
Yes,
showing code.
absolutely.
Cool. Let's see the code.
So,
Now, is this the API you're showing us? Your programming model?
Yeah.
So
Yep.
this is the code that actually implemented this convolution. So actually, let me show you. So this is the
Can you
entire.
make the font any bigger? Or can you see that, Charles?
Good, is that?
I can get in there pretty tightly. I can read it from right here, so
Okay.
it looks pretty good.
So this is the entire code of that program that I was just running that runs in Accelerator.
I'm just going to slowly scan down that.
So the guts of the code is basically.
This is C# code.
This
So this
part
is all
here.
managed code, by the
Yeah.
way.
Okay.
So for the convolution, we just define. So data here is a data parallel array.
Mm-hmm.
So we need, first of all, to convolve it in the x direction, then convolve it in the y direction. So the way we convolve it in the x direction is we go through, this is a C# loop, and every time through the loop, we just shift the image over,
Mm-hmm.
and we multiply it by the factor that we need to for the Gaussian filter, and we add that in to our running sum. And for the y convolution,
Now, one important thing about that is that's adding an entire image. So we're adding two arrays, really, element-wise here. That's
Okay.
what we're doing. So we're not, we're just saying add all elements for each. These two arrays are the same shape. So add each individual element in the same position together to get the new array.
yeah.
Okay.
So that's this is where the aggregate part comes in.
Right.
You're not specifying a for loop. This is, you need to traverse the array in this following way. You just tell us add these two things together, and we say, great, we'll add it together on the
Yep.
order that we want to do it.
Okay. Now, can you show? Now, the type that's doing this magic for me is the DPF float 4. I mean,
Exactly right.
Okay.
Yeah, you should
So,
explain the using stuff up at the top, since that's our library.
Right. Okay. So
We
these
see that.
these types are actually called float parallel array, and they
Okay.
have the long framework names.
Sure.
We tend to just give shorthands for
which
ourselves.
is one of the great things we're using.
Yeah. Right.
Cool.
So yeah, as David was saying, these
Mhm.
these operators right here, this plus, this times, these are actually overloaded operators. So this here is just a number. This is a scalar number. This thing over here is a data parallel array. So when we're multiplying this multiply is multiplying the entire array by a scalar. When we're doing this add here, we're adding two entire data parallel arrays together.
Nice.
So you may ask, how do you do this?
Yeah.
So the key to the implementation is that if every time there's one of these data parallel operations, if we actually went and told the GPU, okay, now go do this tiny little operation, the overhead of communication would swamp everything else. So that's just not a feasible way of doing things. So what's actually happening here, as this program runs along, every time it sees one of these data parallel operations, it doesn't actually talk to the GPU at all. It just records that, oh yes, by the way, eventually when we want to use this result, this is how we will get that result. So it's doing it lazily, or you can call it deferred computation. So the idea is that you keep aggregating these operations, and then in the end, you get to a point where you want to evaluate this now. You want to turn this into an actual C# array. So eventually you want to access it element-wise or dump it out to a file or who knows what. At that point, the accelerator system kicks in and says, oh my goodness, I've been doing all this lazily, and now I got to get on the ball and actually do some computation. But then it has a lot of computation stored up. So we have basically an AST, an abstract syntax tree, just as if we were compiling a program, except it contains precise information about exactly which operations you're doing. So we don't have any guesswork. We don't have any flow control of, oh, maybe it'll branch this way or that way. We have the exact sequence of operations, and at that point we can afford to take some time out, JIT this thing, and we JIT it into pixel shader code, communicate the whole program to the graphics card, and tell the graphics card once, okay, now go and operate on this thing.
Excellent. Wow.
It's pretty cool. And
It's
the nice
very
thing is
cool.
that when you're working with large sets of data, the compilation time that we see is not. It can be significant at times, but we're looking at 10 and 20%. And so you're able, because we're working with large sets of data, to be able to. And our jitter, by the way, is written entirely in C#. So it's entirely user level.
Nice.
So we're able to compile this thing, and we don't have the world's fastest jitter by any means, but we're able to compile this thing on the fly to multiple pixel shaders. So it's not, a lot of the operations can't be expressed with just one pixel shader, and so you actually have to compile them, break them up into multiple pixel shaders. So we're able to do all this, and because the data sets are pretty large, we're able to amortize out the cost of doing the compilation at that time.
Cool.
So, and we actually have a paper on the web that you can actually download.
We'll put the link in the
Yeah,
video
we'll
post.
put the link. So we have a paper that you can download that will describe in lots of detail how we do this. If some of this, was a little hand wavy, and you can actually download our system to play with it too.
Okay.
So we actually have the URL right over there.
Okay. Let me scoot this thing over here.
Sure.
URLs.
And we have a Channel 9 wiki. So
All right. What's the name of the wiki?
it's a Microsoft Research Accelerator project. I think
Cool.
it's right on the wiki page. There's on the wiki page for Channel 9. There's a notion about certain research projects that have their pages up on Channel 9 for people to look at. So it's right in there with that.
Very cool.
And we can post that link too.
Great. So can we spend a little time talking about, maybe the high-level architecture of this?
Sure. Do we want to go back to the other?
Sure.
Go back to my office, and we'll step in front of the whiteboard and just diagram out how it all works.
Cool. All right. Pausing.
So
All right.
let's
We're
see.
back in here.
Okay, so let's see. So I'm going to draw a little diagram of how the system works, and Sid here will keep me honest if I get things wrong here. So here's what so we have Accelerator. Okay, Accelerator. Misspelling. Okay, so we have what happens. I'll diagram this as what happens on the CPU and what happens on the GPU here. Okay, so we have this library. Okay, this just provides a set of operations on what we call data parallel arrays. So you can think of this as it's an abstract data type here. Just an
Okay.
abstract data type, data parallel arrays here. Okay, so what the library is actually doing is, as you make calls into this thing, so you have some calls over here, so you make some calls into this library, what it's doing is it's building up a graph of operations that says, well, here's what I want you to do here. So for example, you might do a plus, you might call plus and a multiply, and you might do something called a reduction, where you're going to sum up all the elements of the array here. Okay, so what happens is you're running along and you're just using this thing like it's just a regular C# library. And underneath the covers, what it's doing is it's building up this graph of operations. And basically what we're doing is because it's an abstract data type, we can put off actually doing the computation. And one of the things that Sid didn't mention is that this is what we call a functional style library. So I think you probably talked to some of the guys doing functional programming at maybe MSR or Cambridge. And so this is in the same vein as that. When you add two arrays, you actually get a new array back. So you don't side effect or modify the existing array. And so this is why this deferred computation is actually really important, because we'd use up all the memory on the GPU really quickly if we didn't, for example, defer the computation. So what happens is you have this library and you're using it. It's a regular C# library, and it builds up this graph here. And this is a data parallel thing, so we restrict the set of operations you can do on this. So the operations we typically allow element-wise operations. We allow reductions, which are things like summing, computing the product. what other kinds of reductions we have there? We have a whole bunch. Max,
Min, max,
Yeah, we have a whole library.
all true, all false.
Yes, all true, all false. So we have element-wise operators and reductions. We have conversions between ints and floats. Okay, and then we have, let's see, we have this. We have Boolean operations here too, so you can do comparisons and things like that. Okay, then we have basic things like matrix multiply, matrix vector stuff. So this is simple linear algebra routines. And then we have something that's a little different. That if you're familiar with data parallel programming, you'll be used to this. But it's, and Sid used this in the demo that he gave. We have transformations on data parallel arrays. So by transformations, we have operations, things like you can shift an array. You can duplicate elements of an array. So when you shift an array, for example, it says take all the elements and just shift them. It's like right shift except applied to an array, or left shift except applied to an array.
Mm-hmm.
So you take all the elements and you just move them over in one dimension a certain amount. Or you might pad the array, you might duplicate it. Now, this is something where there's other people who've looked at doing general purpose programming with the GPU, and this is something that is actually fairly novel about the Accelerator system compared to the other systems that we actually provide these operations here. And the thing is, so why isn't everybody actually already using this stuff? Mm-hmm. You have to learn to think of your algorithm in terms of these aggregate operations. And in particular, you have to learn to think about how you're going to transform arrays and move things around. So if you notice, when we wanted to add all the elements, so what a convolution, let me just go over what a convolution is doing. So convolution is taking a pixel, okay, and what it's doing is it's computing some sum of the neighboring pixels around it. So there's some set of neighboring pixels around this. And what we're doing is computing some kind of arithmetic function of the neighboring pixels. Mm-hmm. So this is how you do things like, you might sharpen up an image this way. You might try to detect, like, a case where you have corners or you have edges and they're sort of blurry because your camera's out of focus. You can use this thing, you sort of look at all the nearest pixels to try to figure out, well, was there an edge here? Is there a big change in color here? Mm-hmm. And so what a convolution is doing is summing up all the things. And one of the things that we did that was a little different is, normally in C you just write, for I equals 0 to, n or something like this, and then you compute the running sum. Sum plus equals, a sub I. I mean, you would do this in 2 dimensions, not just 1 dimension.
Okay.
And then you do this thing. So you write this for loop, and what it's saying is, for every pixel you go through and it says, go sum up each of these things. What we do in our world is we say, okay, here's the image, and what we're going to do is we're going to shift the image around. Okay, and we're going to shift the image around like this, and down like this, and we're going to add up all the sums of these things. Okay, so that's a different way of thinking about the problem. You're saying, what I'm going to do is I'm going to shift the image off by 1, so you shift it off in each direction, you add it all up, and you add up all these images, and the way things work, we just throw away the stuff that's sort of out of bounds, or you have some special case handling for those corner cases. Mm-hmm. But you add them all up, and voila, you've got all the pixels, the convolution of all the pixels, without having to write traversing each individual element of the array. Mm-hmm. And this is what you could say is our method is we're actually allowing programmers to use an explicitly parallel language, or in this case it's just a library. Mm-hmm. And the reason, by the way, we did a library for a certain reason, which is that you can just use this stuff in .NET today. You don't need a new language, you don't need any of that stuff. You can just download this stuff and use this thing as a library. Mm-hmm. Right now we use operator overloading, all that kind of stuff to make it easy so that you can just use it today.
Great.
But to get back to this point, so you actually have to think about these things in terms of these operations, and so you shift these images around and you sum them all up, and that way you aren't over-specifying to the compiler exactly what you're trying to do here. Because if you tell the compiler do things in exactly this order in a sequential language like C, usually the compiler has to do lots of work to figure out that it could do things in a different order and that it's safe. Mm. And in this case, it's like you just specified what you wanted to do at a high level, and then we don't have to go through the trouble of figuring out, oh, it's actually safe to rearrange these operations here. So this is what's really cool about this. And I'll get back to let me get back to how the system works here. So I'm going to erase this stuff down here, which is the operations that we're using. You already saw that. And I'm going to need a little bit more space. Okay, so what happens is you use the library over here. So you make a set of library calls. And underneath the covers on the CPU, we build up this graph of operations that you want to do. And at some point, the user will say, convert this to a C# array, or any managed language. You could actually use any managed language that you want to. So you could write this in C# or managed C++ or Visual Basic, whatever managed language you want to. At some point you say, I need this data parallel array, which is this abstract data type. I need to convert it back to an array that I can actually do something with. That I can do something, display it for the user, or do something like that with. So at some point there's a convert operation in here which basically says, evaluate this thing. I need the result now. Okay, stop building up this giant DAG. Actually give me the result. I need it computed down to individual integers here. So at that point, what happens is we actually do just-in-time compilation. So at that point, we do just-in-time compilation. And so what happens is we actually traverse this whole tree and figure out, well, how are we going to map this to a sequence of pixel shaders? So we just-in-time compile, and I'm sure that you're like, what is he talking about at this point? So we do just-in-time compilation, and we produce a series of pixel shaders.
Okay.
Okay, and we send them over, and the pixel shaders in DirectX, they just end up being a string. And we send this over to the GPU, or we send this over to DirectX, and we tell DirectX, compile this thing. So DirectX actually sends this over, and these pixel shaders are compiled on the fly to the actual GPU. And then we do some of the I lost a step here, which is we do some of the DirectX setup stuff here. So this is the stuff that if you're doing it by hand, you would have to figure out all of this setup stuff. And we just automatically take care of it for you because we're a library, and that's what we do. We take care of all the setup stuff. Good. So we do some DirectX setup, then we compile a bunch of pixel shaders, then we run the pixel shaders, and these things run on the GPU. So this is where things are running on the GPU. And then we actually send the result back to the CPU here. So we actually take the texture, the output texture here, and we move it back to the CPU here. And you've got your result that you can use, and we actually convert this into a C# array, copy the data into the C# array. So that is basically how the whole thing works.
Wow. Very cool.
And we're really pleased that the delayed compilation stuff has worked pretty well. There are some parts where we're still working on it. It is a research project, so debugging this stuff, we kind of wait to do all your operations. So, if you're going to probably wonder, well, how do you debug this stuff? And the answer is, well, it's a little hairy at this point, because if something goes wrong, you have to go and look at the intermediate results here. And we actually have operations for forcing that. But so debugging this is still something we're working on.
Sure.
But we're really happy that we're just able to abstract out all of the gritty details of how the GPU works. And of course, that's what we're about. So it's really cool that here you are, you're writing the C# code, and underneath the covers, all this stuff is happening automatically, which is being mapped down to a pixel shader. And you can see, by the way, that in the future, what you might do is compile this down to a multi-core program. Okay, or you might just, if you don't have a multi-core, you might just compile it down to a optimized CPU program. That's how the future goes. But the nice thing is the library that you're using doesn't change.
Cool. Now, and if the data object is not an image, that's still what you just described is still, makes sense.
Yeah.
It's just a collection of data. That's all an image is, right?
Yep.
Okay.
Actually, the way the interface works right now, for all the benchmarks that we have, including the convolve demo that it just showed, the way we get the image in there in the first place is we just have an array of floating point numbers, and those floating point numbers could just as well be connections between layers in a neural network or whatnot.
Very cool. So what do you want from developers right now? You guys have a place for them to give you feedback? You have some samples they can download and automatically start playing with this stuff?
Yeah.
As opposed to reading a big long white paper?
Yeah, they can download this stuff. We have a few samples. What we're looking for at this point is feedback from people, because like I said, the programming model is not, it's not the standard thing. So we're looking for feedback from people on how well they can use it. We have a wiki set up on Channel 9. We are going to have a community site set up. We don't have it set up yet, but We have they can email us directly if they want to with their feedback.
Okay.
We have an alias set up for that. And we're really looking for people to just try this out because this is a research project. We want people to try it out, give us feedback. We'd also like people to do is to use this to build some libraries on top of because we think that's sort of one of the big areas to go in next for us as a project is what kinds of libraries, because people, anybody who's done a lot of software development, they're going to say, well, I don't program at that low level, I have some library I can use. So we're looking for people who might build up libraries for their particular application area.
Okay.
So image processing is an obvious one, but neural networking, doing scientific computation, that kind of stuff. But most of all, we just want people to try it out and have fun with it and give us some feedback and see how they like it.
Party on the GPU,
Right.
which hasn't always been very easy to do.
Right. And actually, another thing that goes along with it that we're very interested in is expanding our list of application areas where data parallelism is useful. So if anyone has a specialty area of, I'm an expert in figuring out airflow around airplanes or who knows what, and I can do this in a data parallel way, we would love to hear about that because we'd like to expand our set of benchmarks and we'd like to make sure that Accelerator works efficiently in application areas that we haven't thought of yet.
Fantastic. Now, what we haven't discussed is it tied to a particular version of the framework? Is it 2.0? Using generics somewhere in there?
The current version is using generics internally.
No, it's not. It's no.
I'm sorry.
It runs on version 1.1 of the framework and version 2.0.
Okay.
Okay. So we tested it with the older versions of the framework. It runs on the older versions of the framework just fine. It requires for your card that you support Pixel Shader 2.0, which is I think 3 or 4 years old at this point. So most recent cards have used this. Now, if you really want to see performance, if you're a guy who's doing this because you want performance, or you're a gal who's doing this because you want performance, you're going to need a recent high-end GPU card. So to get the performance that we were talking about today. So, but any of the top high-end cards, and if you're a gamer, you probably already own this card.
Certainly.
Because if you're a serious gamer, you're going to have these cards. So, so you need a high-end GPU card to see big performance wins. But you can actually try this thing out on more or less any system that has a recent GPU card in it, and it will run. Some of our samples you may need to cut down the size of the samples depending on the memory on the GPU. But so it's actually fairly. You can download it. It will run on recent versions of Windows. You need the framework 1.1 or 2.0, so there's no requirements there. You will need to update your version of DirectX. Make sure you got the most recent version of DirectX. If you're a gamer, you're probably you know what you're doing here. You got to update DirectX. I think that's about it.
Cool.
And if you don't have Visual Studio installed, you can go get the Visual Studio Express SKU.
So this does work in Express because it's just a library.
It just works in Express.
Beautiful.
Yep.
Excellent.
So you can get the thing in the Visual Studio Express SKU, and you can also just go and download the .NET framework if you're old-fashioned like I am, and you're used to command lines and using older editors. You can just download the .NET SDK and use that too. Cool. If you don't want to go through installing Visual Studio Express. So, and so far, it's worked pretty well. We're pretty happy. We put some effort into testing and making sure it worked on older stuff. I do want to say a few words about sort of what's coming next.
Please do.
So, one thing is, so the question might be, well, what languages can you use here? And obviously, at this point, you can use you have to use a managed language. So you can use managed C++, or you can use Visual Basic, or you can use C#. One of the things we're working on, hopefully, coming sometime this fall, is going to be a native wrapper, so that you could if you're just a regular C++ programmer, you can use a native wrapper for C++. And yes, you'd still need to have the framework installed underneath the covers, but you wouldn't have to learn any of that if you don't want to. So we are aware that a lot of people who do this stuff are interested in C++, and they're worried about C++ compatibility and things like that. So that's something that's coming in the future as a native C++ wrapper. And if you are really impatient using C++, you should go try out Managed C++.
Agreed.
It's really cool. It will work just fine for this.
But I was just going to basically ask, why would you need to create an unmanaged wrapper, in the sense that because in Visual C++ 2005, you write against managed code right in line. So I can have unmanaged code right underneath it. I'm writing managed code because of an attribute I popped on it. Yeah. So as an unmanaged developer, I'm not really. The thing that's different is that I'm importing a managed library, and I have to do Man, I'm not exactly
Well,
sure.
to be honest, we're a little worried about the API being a little chatty.
Got it.
So that's why we're thinking of doing something a bit more sophisticated. And some of those operations that we're doing could be done, in native C++, and then we can move things over. So that's what we're worried about.
Excellent. Cool. Well, this is really exciting. So we'll probably come back and visit you guys in the future.